Hello everyone. Today we're going to be going over some of the popular types of operators on Hilbert spaces, along with some examples and some exercises too. The first we're looking at is the identity. So this is the simplest kind of operator because all it does is map every element of the Hilbert space H to itself. It also acts as a multiplicative identity in this sense. So if T is an operator from H to J, and S is an operator from J to H, we have that IS is equal to S and TI is equal to T. And that's exactly what we'd expect of an operator with this definition here. We also have the zero operator, and that's an operator from one Hilbert space into another. And it maps every element of the Hilbert space H to zero, where this zero is the zero of K. It also acts as a multiplicative zero in this sense. So if I have any map T from K to J and any S from L to H, 0S is equal to 0 and T0 is equal to 0. So I put this remark here that you have to be careful because these zeros denote slightly different things. This zero here is an element of the vector space K. This zero here is a map from H to K, and these zeros here denote different maps depending on which the domain and the codomain of the function zero. So we don't tend to include any subscript on these to denote what kind of a zero they are. It should be obvious from context, but you have to be careful. So next up we have the Hermitian operators. So these are operators on a Hilbert space which are equal to their own adjoint, where adjoint was as defined in the last lecture. These are known as self-adjoint for obvious reasons. And for examples, we always have that the identity and zero are Hermitian. It should be pretty easy to check these from the definitions above. Another important fact, the spectrum of a Hermitian operator is always a subset of the real numbers. In finite dimensions, you'll remember that the spectrum is equal to the set of eigenvalues. So what this says is if we have a operator on a finite dimensional Hilbert space, which is self-adjoint, then it will always have real eigenvalues. So that's a very important thing to know. And for further examples, the standard Pauli operators are also Hermitian. The next property we're going to be looking at is isometry. So T from H to K is an isometry if the norm of Tx is always equal to the norm of x for any x in the Hilbert space H. So what this is saying is that the map T preserves distances and lengths, essentially. So easy examples are on the Cartesian plane R2, rotations and reflections. If you picture a shape rotating around in the Cartesian plane, you're not changing any of the lengths there. So here's another important thing you need to know about isometries in the case of Hilbert spaces. So an operator U is an isometry if and only if for every x and y in H, the inner product of x and y is equal to the inner product of ux and uy. So not only does U preserve the norm, it preserves the inner product as well. So this is a nice exercise to try at home as well. The next one, isomorphism. So these are also known as invertible operators. So these are operators T from a Hilbert space H to a Hilbert space K, for which there exists some S such that TS is the identity and ST is the identity. And S is going to be an operator from K to H in this case. Now, we write S is equal to T minus 1 in this case. And we'll just note here, not all operators are invertible, so you can't always just write T to the minus 1 for any given operator T, as nice as that would be. So easy exercise. If T is invertible, then its inverse has to be unique. We use this notation to say that H is isomorphic to K, which means that there exists an isomorphism from H to K. If we have an isometric isomorphism, we use this notation. And as a medium exercise, I've said show that this and this relation are equivalence relations on the class of Hilbert spaces. So well done if you get that one. The next type of operator we're looking at is the unitary operator. Now this is an operator on a Hilbert space for which its inverse is equal to its own adjoint. Now, there are always isometric isomorphisms, but there do exist isometries that are not unitary. So an exercise I've left for you is to find such an isometry that is not unitary. In quantum computing, the set of unitary operations on the state space, which is always a 2 to the n power of the complex numbers, form the possible operations applicable to the n qubits of the system. Now, the word possible is perhaps doing a bit of heavy lifting here because there are some gates which are just going to be completely unrealistic to achieve, especially with the computers we've got today. But in theory, they are theoretically possible to have all of the unitary operations be the gates available to you on this n-qubit system. The set of all unitary operations on a Hilbert space forms a group with operator composition and identity equal to the identity of H. I've left that as an exercise to prove as well. It's not too hard at all, but some thinking has to be done about the properties of composition of operators which are unitary. Another important fact about the spectrum of a unitary operator is always a subset of the unit circle. And so this is just the notation for spectrum here, sigma t. That's a subset of the set of complex numbers with modulus equal to 1, which can also be written in this way. Now this will take a little bit more of a involved approach to prove. I think you need to refer to the Carl Neumann series, for instance, so we've not included the proof of this here. But later down the line, if people are interested, we could definitely go through that with you. A normal operator is an operator T on a Hilbert space which commutes with its own adjoint, meaning that T star T is equal to T star. So unitary and Hermitian operators are normal, and that's quite easy to see just by these properties here. But as an exercise, try and prove that the skew Hermitian operators are normal. So these are operators for which their adjoint is equal to their negative. Next, we're talking about the rank 1 operators. So an operator T from H to K is rank 1 if it has one-dimensional image. Now, an interesting consequence of the Riesz representation theorem is that for these operators, there exists U in H and V in K such that Tx is equal to the inner product of x and u times v for every x in the Hilbert space. So you can always define a rank 1 operator from H to K just by knowing a single element of H and a single element of K. T is finite rank if it's got finite dimensional image. And an interesting property of these that's very useful in practice is that finite rank operators are always expressible as linear combinations of rank 1 operators. So a compact operator is an operator from H to K for which every bounded sequence in H yields a convergent subsequence in K. So if I have xn in H which is bounded, then I know that Txn has a convergent subsequence. So equivalently to this notion, you say that T is compact if the set T BH is compact. Now BH here is the notation I'm using for the closed unit ball of H, defined as such. So this is a compact in the standard sort of topological setting. So for an exercise, now this one is very useful. If T is compact, then so is the composite STR for every S from K to J and every R from L to H, where these are two more Hilbert spaces, L and J here. Another interesting property is that all compact operators have compact adjoints, and all finite rank operators are compact. Now, you might be able to prove this one on your own just by sort of looking at the fact that these have finite dimensional image and then using the fact that in that setting, being compact is equivalent to being closed and bounded. So recall that for a Hilbert space H, we can take any closed subspace L of H, and we can write H as a direct sum of L and L. We call this perpendicular, short for. So we can write H as a direct sum of L and its complement here. The projection PL as an operator on H is the function which maps sums in this direct sum L plus L dashed, where L is in L and L dashed is in L's complement. It maps these sums to L, so it just kind of like chucks away whatever part of it was living in this complement section. So one property of our projections is that they're idempotent. So PL times PL is equal to PL. And as an easy exercise, I've said show that PL times PL complement is equal to 0 always, whenever L is a closed subspace of H. Show also that these projections always have norm 1, well, whenever L is not 0. If L was 0, then this would have norm 0, but then it would just be the 0 map anyway. Finally, that brings us to the tensor product of two operators. So if T is an operator on H and S is an operator on K, we write T tensor S as an operator on H tensor K for the operator which acts on the pure tensors H times K for H and K and K, as you would expect. So H tensor K gets mapped to TH tensor TK. And we just extend this by linearity so that it's active on the entire space H tensor K rather than just on the pure tensors. So we'll note that not every bounded operator on H times K is formed in this way. So as an intuition for those of you familiar with quantum information science, not every gate on an n-qubit system can be deconstructed using only 1-qubit gates. So the only gates which are kind of this form of big tensor products are the ones which can be enacted in parallel on all of the qubits. And the entangling gates are the ones which cannot be written in this way. So this is kind of one of the important things about quantum computing, which is what makes an n-qubit system so much more than the sum of its parts. Thanks everyone for listening. We'll be back with the physics on Friday. If you've got any questions about the material or about the exercises, you know where to find me in the Zulu. Cheers, guys.